I'm Garen Lees, and I'm going to be talking about how ODE has been engineering successful offshore wind farms for the last 20 years. ODE is part of the Doris Group with over 55 years experience in offshore oil and gas and over 20 years experience in offshore renewables. We cut our teeth on the early projects in the UK before moving on to projects across Europe. Today, we are active in all the offshore wind markets, having been involved in projects in 17 countries, totaling over 40 gigawatts in capacity. Our engineering and project management expertise reaches across the full life cycle, from concept and feasibility studies in environmental, geotechnical, at consent stage, through to FEED, detailed design, and full project management services across the development and construction phases. We're experienced in turbine foundation design, fixed and floating, mooring systems, anchoring systems and cables, offshore substation design, and the supply of expert personnel through secondments into positions throughout the project lifecycle. We assist developers through the provision of owner's engineer and project management services. Current projects include wind farms in Poland, Ireland, the United Kingdom, and across Asia in South Korea, Taiwan, Japan, and Vietnam. We provide engineering service such as concept design, FEED, and detailed design to individual projects across developer portfolios and through frame agreements. Moving on to floating wind farms. We draw on our oil and gas experience of floating production systems, FPSOs, in deep water and ultra-deep environments. The decades of designing, engineering, mooring systems, anchors, umbilicals, and cables is all directly relevant to floating wind. Our specific expertise covers mooring systems, design, and structural design. Floating offshore wind turbine mooring systems present specific challenges that need to be carefully investigated. Those are significant movements due to storm waves in shallow water, potential slack snap loading, and fatigue performance of mooring components. We can assist in the analysis, design, and mooring system configurations, including material selection based on floater design, water depth, and ground conditions. A large track record in mooring system engineering inherited from oil and gas. The expertise we bring covers the full mooring systems from seabed to surface, anchors and piles, subsea connectors, chains, wire ropes and synthetic ropes, fairleads and tensioners, and auxiliary components. We have the experience in static analysis to pre-design the floater support structures, and extreme fatigue analysis based on complete structural models and the following load combinations: hydrostatic pressures, hydrodynamic loads, aerodynamic loads, and mooring loads. Aero-hydrocoupled analysis to study platform motions. Our analysis is based on fully coupled models of floating wind turbines and analysed with fast and OrcFX software to take account of simultaneous wind and wave loads in a time domain study. In order to define the best concepts regarding specific site conditions, we can provide a screening study of different floater concepts, definition of the floating platform arrangements, a preliminary sizing of the selected floating platform concepts regarding stability criteria, and design optimized using generic algorithms. Our oil and gas experience in cables and umbilicals allows us to apply that experience to the dynamic cables that are used in offshore wind. Related to this, we also have extensive experience designing offshore substations, and we bring these factors together to allow us to optimize designs for floating substations as well. So far, we've talked about our owner's engineer our project management, and our design engineering capabilities. This all comes together in the deployment of floating foundations, and within our group, we can also undertake tank testing and the proving of concepts at our facility in the south of France. All this comes together to help us select the correct foundation and the global system for a given environment and the development objectives of the developer. With detailed analysis of the merits of each system that then plugs into the field development plan, allowing us to select the best combination. Moving on to our floating foundations. Our first floating foundation is possibly one of the cheapest ways to deploy floating wind in the water depths of 70 to 250 meters with large turbines. The AWC is a concept which consists of a concrete column made with simple slip forming techniques and the potential to be used in a wide variety of docks, ports and harbours with high local content. It is a robust and proven technology. The AWC is based on a technology that we developed over 50 years ago for the oil and gas industry. It was used in the North Sea extensively with 13 different articulated columns deployed in steel and also in concrete. The mooring articulated column on which the AWC is based was originally installed in 1982 and then decommissioned almost 20 years later in 2001. Also in the 1980s was the Northeast Freight control platform, which was permanently manned with personnel on the platform. The AWC itself consists of the turbine, the concrete column, which in the configuration we're showing is 15 megawatts in 110 meters of water depth, is around about 9,000 tons, and then a concrete base of around about 8,000 tons, into which we fill ballast to allow us to maintain the gravity structure on the seabed. The articulated joint itself is around about 270 tons. The components of the articulated wind column are, again, the column, the articulated joint, and how we get the cable up through the center. And that mirrors how we did it in the oil and gas application. The advantage of this is that because the cable comes up through the center of the column, we need a relatively small dynamic cable that allows us to reduce cable fatigue and allows us to have a more reliable system overall. Looking at construction methodology, we build the AWC using simple slip forming techniques. So it's rather like building a lift shaft or a bridge. So it's something that is readily adaptable, and it's something that we've got a long experience of, having done this in the North Sea and elsewhere for oil and gas installations which were formed of concrete. The production process itself, our preferred material is concrete, but steel is a viable option, and we look to batch manufacture using a process which allows us to produce one finished unit every week, and that requires to have 4 units in production at any one time. This is obviously based on availability of land in quayside and water quayside availability. The gravity base itself is constructed on a floating pontoon, which allows us to do both the gravity base and the column itself a single production unit. Looking at this in a little bit more detail, the example here is of the mooring column being built at the facility we had in Scotland during the 1980s. We built it there and then uplifted it using a gantry crane, which allows us to manufacture the AWC in segments. Once constructed, installation is a simple affair. It requires the minimum seabed preparation. It can accommodate uneven seabeds. There's no need for piling, and it means there's a very low impact on marine life. It doesn't need a great deal of specialized vessels, and the foundation itself is largely unaffected by scour. When we take it out, we mate up the base and the column at the quayside, and that requires a relatively shallow quayside compared to a number of the different semi-submersibles. Once it's taken together, we then tow it out to site using harbour tugs or anchor handling tugs, at which point the gravity base itself is weighted down and sunk slowly to the bottom, and the column is ballasted while the ballast that goes into the gravity base is inserted. Once this is complete, the foundation is now in situ, and those are done as a campaign, and we can come back with a heavy lift vessel to install the fully formed turbines. In this case, we've done two studies, one with Saipem and with Herma, and in both cases they came up with roughly the same options, and that is that the heavy lift vessel will moor alongside the AWC so that both vessels move in tandem. That allows us to safely install the turbine onto the foundation, which at this point is acting as if it was fixed. Some images of our previous installations. So this again is the mooring column in fabrication, then tow out, upending, and installation. One of the key features that we need to look at here, and particularly relevant for ongoing licensing rounds in the United Kingdom, is its small footprint. It requires only about 30 meters by 30 meters to support the entire AWC, whereas we can compare that to a spar type arrangement where the same size of turbine may require up to 800 meters, sterilizing a large area of seabed, which has, particularly in power-to-platform applications and also areas with fishery concerns, a large impact on the other marine uses that can be achieved. Finally, on the AWC, it's also available as a substation, which will allow us to produce a substation of up to around about 850 megawatts on the same foundation as the turbines, and is also available as a hydrogen production variant, which we'll come on to that in a little bit more detail. Our second floating foundation that we're going to look at here is Nearwind, and this foundation is a development of the semi-submersible designs, and here we've got two options. One's a 3+1 and a 4+1 design, where the turbine is in the center of the multi-column design. It has attenuation chambers, and it can be produced of either steel, concrete, or hybrid alternatives. And again, this is designed for the very largest turbines. The multi-column design using double trusses is adapted for higher end WTGs, and currently we're looking at a minimum of 8 megawatts and up to 15 plus megawatts, and that's using the steel or concrete variants in either 3 or 4 pontoon designs. Looking at it in a little bit more detail, we generally find that semi-submersibles without some sort of dedicated motion reduction device results in a foundation that exceeds the wind turbine's maximum motion criteria. And our experience dating back to the 1990s shows the benefits of extended skirts and attenuation chambers, and we've applied that to the Nearwind concept. The experience on numerous projects from floating LNG, FPSOs, and now floating wind, together with tank testing, demonstrates the efficiency of side skirts and attenuation chambers in controlling motion responses. And we've demonstrated this both electronically and in our test tanks as well. In developing the best performance, reliability, and cost outcomes, the group has investigated several design alternatives. and we apply these through the modelling that we've done on Nerewind. This product evolution leads to Nerewind semi-submersible with truss beams for best performance in class. It's available with either 3 or 4 plus 1 versions and a central WTG. And we see overall lower inputs, better motion performance, a low unit cost per megawatt, lower capex versus standard semi-submersibles, and improved operations and improved production parameters. The design has been optimized for reduced maintenance and an extended design life, and critically, better through life LCOE performance. Moving on, now taking a look at our green hydrogen production from floating wind, a project that we're heavily involved with. We've been working extensively with ERM on the ERM Dolphin project, and that is a UK government funded project for the supply of deep water offshore local production of hydrogen. And our partners on this project are ERM, who are the project leaders, and we're involved with Doosan, Tractable and Vestas, and of course Principal Power, who are providing their foundation. The objective with this project is to complete the demonstration phase, where we look to use a 10 megawatt turbine to produce 4,000 kilograms of hydrogen per day, and this will be connected using a 3-inch pipeline back to the Aberdeen hydrogen facility. I'm going to take you through a little bit of detail on how this works. First off, we modelled the options for the distributed hydrogen concept. The options there were Dolphin, a separate offshore hydrogen production facility, and then bringing the power back to the beach for onshore hydrogen production. And with parameters that we have for the remote location, for example, island locations, Dolphin looked like it was one of the better options. It didn't have the high costs of very large offshore production facilities, nor did it have the high losses of bringing the power back via a cable and then producing the hydrogen onshore. So our role was to marinize or to find a way to marinize the hydrogen production and get the elements of the hydrogen production onto a floating foundation. So that was desalination, the electrolyzer, the backup power, and the hydrogen storage, and then of course the export itself. Looking at that in a little bit more detail, the equipment that we have on the ERM Dolphin project is the seawater inlet. We need to take the seawater in, we need to clean that water up, that's filtration, then desalination, which eventually gives us a freshwater output, which we can then use for the electrolyzers. The electrolyzer we're using is currently based on a 10 megawatt, so we're right up there with the same megawatt nameplate as the turbines as well. Outputs from the electrolyzer is oxygen and also the hydrogen, of course, and that is at 30 bar, and that's enough for us to be able to pump it back to the beach in this scenario. What we're looking to do is to compete first with blue hydrogen, and then also with grey hydrogen, and then also with blue hydrogen. The commercial targets are between £1.50 and £1.90 for a kilogram, and the prototype at 4,000 kilograms per day will be around about £5 to £6 per kg. Now, with the current gas prices in the UK, we're already very competitive with blue and certainly with grey hydrogen as well. The commercial wind farm that we're looking to do will be ultimately towards the north of Scotland, where we hope to be able to develop a facility of up to 4 gigawatts in electrical production, and then that will join the network of gas pipelines which are already in existence across the North Sea, allowing hydrogen to be taken back to the St Fergus power station in the northeast of Scotland. we've now looked again at our demonstration project, so that will be located in the northeast of Scotland, adjacent to the Kincardine floating wind farm. And that allows us good communications in terms of facilities of offshore wind farm. But critically, it's close to a market point. So our export route is back to the Aberdeen hydrogen facilities, which allows us for a relatively short pipeline, and that feeds into a system that's been set up for the supply of hydrogen to local buses, and eventually we'll also be looking at that into a system where we can provide that into other off-takes. So in this case, we're looking at other applications at relatively low production volume so far, but it's injection into the grid, it's export by road tanker, and then bottling and use for industrial purposes, farms and so forth, which are not necessarily grid connected. And that will be the next stages as we're looking forward. So hopefully I've been able to take you through ODE's capabilities in offshore wind, in floating wind. I look at what we're doing with two different foundation types, and also what we're doing in hydrogen. These are all backed up by our expertise in engineering and project management. Thank you very much for your time. Contact details on the screen. Please ask any questions that you have, and myself and the team in Korea will be very happy to get back to you. Thank you very much.